Hi everyone, I wanted to take a few minutes and introduce you to a few basics dealing with one of the most common controls you'll run into in the HVAC world, and that would be relays. So let's take a look. They come in many formats and they can look very different, but some of the most common are known as 340 relays made by Zettler, due to the 340 or 340 at the end of the part number. You also have what's commonly called as fan relays. They look something like this. They can have a coil on one side and anywhere from 2 to 6, sometimes rarely 8 terminals for you to hook up a source of power and switch between legs of power or speed, for example, on a blower motor. And very similarly, works very similarly, is the commonly referred to as ice cube relays, which are general purpose relays. So let's start by looking at the most common, a 340 relay, and their brothers, which are the 341 and also another relay. I don't know if I brought a picture. A 341 and a 342. The biggest difference being, if you look carefully, is the voltage required to control the coil. So on a 340, your coil is considered 24 volts. Here on a 341, your coil is 120 volts. And on this one, at 3/4 horsepower, 120 volt, coil is 120 volts. So be aware of that. We know that 90% of the control voltage in a residential system is 24 volts. However, that changes very quickly when you get into commercial, heavy commercial, and industrial equipment. You very quickly start dealing with control voltage such as 120, 240, and sometimes 460. So you need to remember to always look at the tag before you proceed, because if you have the false sense of security that you can treat this as a 24 volt coil, if you notice, they look identical. The only difference is the tag where you'll find that information. So do not assume it's a 24 volt coil. Okay, let's look at how a relay works. And when I say relay, I simply mean how a device or a control that will switch on and off a piece of equipment or a function of equipment, such as a blower motor, condenser motor, heaters, things of that nature, how they function. In the 340 case, you'll find a relay printed right on the top or the face of it. It's difficult to see, but you'll see 1, 2, 3, 4, 5, 6, and you'll see usually a tag listed on the side of it. This wiring diagram shows you its normal positions. In this case, we have a relay that has a normal position of normally open from 1 to 3, if you can see there, and normally closed 1 to 2. Interestingly, like many, this relay has 2 switches. Here's one switch, 1, 2, 3. Here's your second switch, 4, 5, 6. On the second switch, 4 to 6 is normally open, 4 to 5 is normally closed. And down here at the bottom, we have our coil. So what that simply means is, when this relay is sitting in a piece of equipment and there is no 24 volts present at the coil, meaning you do not have common and a hot 24 volt line energized, then 1 and 3 will be open, 1 to 2 will be closed. But as soon as you do receive 24 volts to this coil, that will reverse. 1 and 3 will close, 1 and 2 will open. If you're using 1 and 3 to turn on a blower, as soon as it closes, you can turn on that blower. If you would like, you can use 1 and 2 to turn something off if the condition calls for it, if something else is energized. So there's a lot of functions in these general purpose relays that you can use them for. And I've seen them used in very, very creative ways, such as a reversing valve put in backwards, and you can use, so if a reversing valve is put in backwards and it's programmed incorrectly, it would simply, anytime you wanted cooling on the heat pump, it would heat. Anytime you want heat on the heat pump, it would cool. And I've seen a tech early in my career use a relay to fix that problem. So very creative usage out there, but it is so vitally important that you understand that you must first look at the tag to determine what's going on. So let's talk about the tag a little bit. Every tag will give you a few vital points of information. For example, on this tag, we find our coil is 24 volts and it's a 50 to 60 hertz contactor, which means it can be used in our market in the United States, which is 60 hertz equipment. But if you remember, in Europe and most the rest of the world, they use 50 hertz or 50 cycles per second. So it can be used in both cases. It also lists the lock rotor amps and the full load amps. And depending on the voltage you're using, that will vary. So for example, you can have 82.8 lock rotor amps or 13.8 full load amps once everything's running if you're using 120. But that will change to 39.6 lock rotor amps and 6.9 full lock rotor amps if you're using 240. Likewise, you can, on this particular relay, use all the way up to 480 volts. Do not assume that is the case for every relay. Many of them are not heavy duty relays that cannot use 480 volts. What does that mean? So we know we have 24 volts on our coil here. If you ever wonder which one's the coil, it's the terminals that you can, if you look closely, you can literally see them soldered to the coil itself. So this connects this terminal to the coil itself. The coil, if you hold it to the side, is fairly easy to see. Oftentimes it's not wrapped. This one's wrapped in blue protection, blue insulation, but oftentimes it's not wrapped and it's just a copper plated collar coil, or just a copper wire wrapped around creating the coil, this collar. And you can see the solder where your common and your hot wire is soldered to the coil itself. So it'll look something like this, or it could possibly be a little heavier duty and look like something like this. Now, that's your 24 volts. We know that. However, that does not mean you have to use 24 volts to switch the power or the leg on this relay. For example, in this switch, 1, 2, 3, 1 is your common terminal. And all I mean by that is at some point, 1 will touch 2, 1 will touch 3. In this switch, 1, 5, 6, 4 is your common terminal, simply meaning 4 will touch 5, 4 will touch 6. At some point, whether there's 24 volts or not, it'll change back and forth or switch. You can use on your common terminals 1 and 4 on this relay 120, 240, 277, or 280 volts. If you're dealing with a typical magnetic motor. Now, you'll see down here, you'll see 15 amps RES 120 volts, 15 amps RES 277, 10 amps for 480. That means resistive load. That's referring to something like a electric heater in an air handler, electric air handler, or an electric furnace. Notice it says 15 amps in a resistive heat load of 120. Let's use the most common. You have a 240 volt air handler with 15 kW heat. Each 5,000 pulls 20 amps. Can you use this relay on the heat kit of a typical air handler you'll find in anybody's house? The answer is no, because each heater is going to pull 15 or 20 amps. Your max rating is 15 amps on a resistive load, so it would not work. Be aware of that. If you wanted to use this to turn on and off a heater, you would need a heavier duty relay. And oftentimes that's why you would never use a 340 in that application, because we'll use heat relays or sequencers that are designed to handle that resistive load. So some other things to consider: diagrams can vary on relays. As you're learning how to read diagrams, it's important to understand that not all companies, not all electricians, not all diagrams are the same. They can vary slightly. For example, this diagram is pretty self-explanatory. 1 is not touching 3, 1 is touching 2. Another example, on this fan relay, same thing as we have here. On this fan relay, we have 1 and 3 are touching. What does that mean? 1 and 3 are touching and going through the coil, the resistance of the coil. So we know immediately that 1 and 3 are our coil. That's where we would place our 24 volts, common and hot. Or say, for example, you wanted to turn on the fan for a blower motor, we would place common on 1, and we're using G to turn on our fan. We would place G so that when the thermostat energizes G or closes R to G, red to green, then it would change the normal position of this relay. In this case, if we're looking at it, we have 2 and 4 are normally open to 5 and 6. As soon as it's energized, this will change, and 2 and 4 will be energized to each other, and 5 and 6 will open. So at the moment, 2 and 4 are not touching. This slide will slide to the right. This bar will slide to the right. 5 and 6 will open, 2 and 4 will close. What do I mean by bar or tab? Inside that relay, you'll have a bar or tab. Ice cubes are a little different. Here's a common example of an ice cube diagram. They're hard to see. Most of them are clear, so I found one that kind of shaded the diagram portion. Again, we got to look at our criteria here. Do not assume the coil is 24 volts. For example, in this instance, this is a heavy-duty ice cube general purpose relay. The coil will not close until 220 volts are applied. Now, how do we know which terminals on this side are the coil? If you look at the bottom, 13 and 14 touch. They're going through a little resistance. We got our coil here. Compare that to this coil. Or oftentimes you'll see a coil where it wraps around as compared to, say, this one doesn't even give you an example of the coil, but it can vary somewhat relay to relay. Do be aware of that, but I really love ice cubes in that you can see the contacts. If they're burnt up, here's your contacts. If they're burnt up or if they're needing replaced. You can also see the coil is connected. There's that solder again. So this terminal right on the other side would be my coil, one side of my coil. You're going to get the same thing on 14. So let's look at that again at another angle. Here's how all relays work. You can see it's soldered. Here's going to be one side of my coil. The other side's on the other. And here is my common terminal. What do I mean by common? If you follow this terminal through the relay, it is attached to this bar that will actuate. It'll go left to right depending on does it have 24 volts. Currently, this bar is touching this terminal. So let's name them 1, 2, 3. 1 is my common, and it is in its original position with no power applied, it is closed to 3. So 1 is closed to 3. We're making contact on this blade, so power will come in, flow through this blade, and come out this terminal. As soon as you apply 24 volts, that blade will switch to the right, and it will open 1 to 3, and this blade will close to 1 to 2. So power will come in, go down the blade, and make contact here on this 2 terminal. Now if you notice, this is one switch, 1, 2, 3. If you turned up on its head, it would have another switch. You could label 4, 5, 6. That should make this diagram look a little more logical. In this case, we have a total of 14 terminals we can plug onto. We have the commons are 9, 10, 11, 12. Coil 13, 14. Why are 9, 10, 11, 12 the commons? Notice this diagram. Currently 9 is closed to 1. As soon as it's energized, it'll close to 5. So you would read this diagram as 9 is normally closed to 1, normally open to 5. So you would bring your power, your whatever you're controlling, and power this switch on 9, because it will at one time or another touch both 1 and 5. Similarly, 10 is normally closed to 2 and normally open to 6. If you can see this switch signal, it's closed to 2. It will switch to 6 when 220 volts are applied to the coil. 11 is normally closed to 3. It'll switch to 7 when you apply voltage. 12 is normally closed to 4. It'll switch to 8. Or 12 is normally closed to 4, normally open to 8. So you need to learn how to read these diagrams, regardless of which type you have, and understand that they work in the exact same function, exact same way. For example, here's our coil. In this case, it's a 24 volt coil. If you can read upside down, oftentimes you have to. And our common and our hot would, actually that says 2 and 4. So here's our 2 and 4 terminals. Don't make that mistake. We can assume this is our 1 and 3 terminals. So our coil is here. And then normally 2 and 4 are open, but as soon as it energizes, this bar will close inside and it will close 4 to 2. All right. Something else to be aware of. You'll often hear phrases such as single pole, single throw, double pole, single throw, double pole, double throw. And you need to be able to recognize what we mean here. So if we take a standard 340 relay, we see the coil on the bottom, right? Here's common, here's hot, 24 volts. And then here's one switch, and here's another switch. 1, 2, 3 makes one switch, 4, 5, 6 makes one switch. So the question would be, how many poles are on this switch? How many throws? And a good way to understand this is to look at this diagram. If you have one source of power, that's one pole. And if you're making one switch, either normally open to close or normally close to open, that would be a single pole, single throw switching relay. If you have one source of power and you're making two switches from normally closed to normally open, and you can also close from normally open to close, then you have a single pole double throw. If you have two sources of power, so let's say you have two blower speeds and you're powering C1 with one source of power and C2 with another, but you can only close one switch, either from normally open to normally closed, then you have a double pole single throw switch. And then finally, two sources of power, and you can close both from normally open to normally closed, then you have a double pole, double throw switch. So you'll hear those terms. So let's consider what we have here. We have a common on 1 and a common on 4. Again, why are they common? One at one time or another will switch from 2 and switch from 3. It can touch 2 and 3, but 3 and 2 will never touch each other. They have nothing in common with each other, but they do have one in common with one another. So 1 is our common. This is where we'd power our switch. Normally close the 2, can open the 3. 4 is our common. Normally close the 5. When 24 volts is applied, this will switch and close the 6. So this would be a double pole, 1, 2, double throw, 1, 2, switch. I'll go over that in more detail, but it's important to just begin to understand what double pole, single throw, double pole, double throw, single pole, double throw, whatever configuration you have, what options that relay will give you. There are many other kinds of relays, like sequencers, for example, and a very common one used in HVAC is known as the ICM 102, or a time delay relay. This works like any other relay except for instead of opening and closing immediately, you can set a timer anywhere from a fraction of a second all the way up to 10 minutes, or a fraction of a minute, few seconds all the way up to 10 minutes, where it will close the wire 1 to 3. Don't let me confuse you. When you're placing a wire on a relay, you are merely breaking one wire. Okay? You will never put 2 opposing legs on a relay that can touch each other. So one of the most common mistakes early techs make is that they'll see 2 wires coming in and they think they have to be plugged onto a device, whether it be a relay or a switch or whatever. No, every control, every safety, with very few exceptions, all they do are break one leg of power. So if you have L1, L2, and you don't want that circuit to operate, or you want it to turn on, all you have to do is break L1. Okay? You can send L2 straight to the blower motor, for let's say, and then stick L1 through your switch. All right? If it's normally open and you want it to turn on, you close it. If it's normally closed and you want it to turn off, you open it. And you do that through the switch. So from 1 to 3, let's say we would have L1 broken through 1 to 3. L2's sitting at the motor ready to go. L2's there. But that motor will not run unless it has both L1 and L2 energized at the motor. Okay? So I know that's something a lot of my guys struggle with, but do understand that every control, every safety, with few exceptions, will break one leg of power. You cannot touch L1 to L2. Okay? You must keep them separate in the circuit. They will meet at the windings of the motor you're trying to start. Another very common form of relay are the ones that are actually soldered on the circuit board. And I just wanted to kind of point this out. We're going over all the resistors and capacitors that you'll find. Here's a little capacitor. Here's some resistors. The various things you'll find on a board. But if you don't know yet, oftentimes these relays are soldered directly into the board. And you can usually kind of tell what the relay's for. For example, this is a furnace board. You follow this relay straight across and you notice you have humidifier and electronic air cleaner terminals. So this relay is going to turn on and off our electronic air cleaner terminals. In this instance, let's look what we have. We follow it right across. We have continuous blower speed, cooling blower speed, heat blower speed. So this relay, we can logically infer, controls the speed of the blower depending on, is it in heating mode, cooling mode, or if you just go to your thermostat and switch fan to on, which would be your continuous blower. And then up here we have HSC. You can infer, let's see, that might be, say, a hot surface igniter. So we're breaking one leg of our igniter through this relay. But whatever you find on a board, these relays can go bad like any other, and they commonly do. But I want you to know, if you run into this, you don't replace the relay on the board unless it's plug and play, because the labor involved, the time it would take to order the relay, carefully unsolder the burnt relay, and then solder in a new one. By the time you do that, you've charged the customer more than it would cost to replace this circuit board. Even let's say this circuit board costs $700-800. You're talking about hours and time spent to replace these relays. We don't do that. We actually just replace the entire circuit board if any one of these go bad. Or if you get good enough, say our blower relay goes bad, I can get a 3-switch relay. 3-switch, what do I mean by that? Something like this. This has 1 switch, 2 switch, 3 switch, 4 switch. I can get a 3-switch relay and rewire through that relay to keep them going with blower speed while I order a new board. Oftentimes you'll use relays just to get people functioning until a part can come in. So another example might be an ECM blower motor goes out and you want to put in a PSC blower motor, a regular blower motor. You'll use that relay to turn and cycle that blower on and off while you wait for your ECM motor. So a lot of functions, very common part. You're going to run into them during your career, and you will replace hundreds or thousands of them while you're running service. So it's very important to understand how they function and how they work. We will work a little more in detail in class, but I hope you have a slightly better understanding of how relays work. And if you have any questions, please let me know.